Okay, so we'll continue. So it's very interesting to learn what you guys all thought was the best fuel. So I think it's nice to know chemical kinetic modeling because if you ever have an idea about an interesting fuel like a performance acid, you can build a model for it from your knowledge of the subject, and you can see actually in a simulation how it works and if it makes any sense. Of course, you cannot think things like producing the fuel and transporting it. Those are outside the field of chemical kinetics. But still, I think interesting to know how a fuel burns using these principles. So this is kind of the general approach we would use if we want to build a new model for a new fuel. First, you got to generate your list of elementary reactions, okay? And this is, again, all the elementary reactions which you think are important, and based on the understanding of the field and the subject, the most important reactions, and assign rates for these chemical reactions. Now, of course, the different types of reactions, as we'll see, might be different depending on the engine, depending on the mixture fraction, the temperatures, the pressures. So this list is a postulate. It's a hypothesis. There's no such thing as the right set of elementary reactions. Okay, that's there's countless possibilities for the reactions one can include in a reaction set. So actually, Professor Green from MIT has a code called RMG, Reaction Mechanism Generator, and it's a rule-based approach. It kind of explores, based on some kind of principles of chemical reactions, all the different pathways that are possible, but then it constrains it. It constrains it based on the temperature that's provided, maybe the mixture fraction, the residence time, and so on. So otherwise, if you just say, generate a list of chemical reactions, it could be millions, tens of millions of potential reactions. Some of them might be too slow, might not make any sense. Some might be very fast, which are important to include. And so the list of chemical reactions, we have to understand, it's a hypothesis, it's a postulate. It's not a definitive answer, okay? And it's one that you have to provide based on your knowledge of the system, okay? And then we assign rates to those reactions. Now the rates are things that could be calculated from quantum chemistry or based on rules, and we'll talk about that as well. Then you need thermochemical data for all the species in the different reactions. You need to know what is the thermochemistry, what is my heat capacity, my entropy, my heat of formation. And similarly, if I want to simulate combustion in a reacting flow, like a counterflow flame, a premixed laminar flame, we need transport properties. We need the diffusion coefficients, we need the viscosity, we need all that information to calculate the mixing at the molecular level. So these two first steps are just to build your model, but again, a model is only a model unless you've tested it against something. So we conduct experiments, validation experiments, and different types of experimental reactors or flames. We then simulate those experiments using something like a Chemkin, Cantera, different codes that are available for simulating the different experiments. An important thing to note is these validation experiments, they're in systems which are kinetically controlled. They shouldn't be a system where fluid mechanics is a dominant feature of the system, or mixing is a dominant feature. So typically, they're homogeneous. If they're not homogeneous, they're one-dimensional, so you really confine the mixing process to diffusion-controlled systems like a counterflow diffusion flame, or maybe the most complex would be a 2D laminar diffusion flame. But again, the simplest form, laminar, no turbulent mixing, things where you know that the kinetics are the governing phenomena of the observations that you're making. And then you simulate those kinetically controlled experiments with a computer model. The inputs to that model are the physics of the system, the initial temperature, the initial pressure, the mixture going into the reactor, and then the physics of, is it a batch reactor, a stirred reactor, a flow reactor, a 1D flame, and so on. And then the other inputs from the model side are the kinetics, the kinetic data, the thermodynamic data, and the transport data. You do your simulation, you compare the two, and if it's a satisfactory agreement, you can stop. You can say you have a good model, but oftentimes it's never satisfactory because The first set of reactions might be missing some reactions. Probably some of your kinetic data and thermal data is wrong because it's just a first guess. So you can do some sensitivity analysis. You can find out the important reactions, the important thermal data, and you can try to improve your model. And it's an iterative process. It's an iterative process, not even by one individual. It sometimes takes a whole community of individuals iterating until you come to a reliable model. And this process has to be done for many different fuels and across many different conditions. And this is a chart that shows how the conditions of your reactor really determine the types of reactions one has to include and why it could be so complex. So this is for a very prototypical molecule. We have here N-heptane, so the one up there, C7H16. Again, for many combustion systems, for alkanes, we choose N-heptane as your standard molecule. It's been studied a lot. Professor Pitch from Aachen, he'll say that N-heptane is you have the best kinetic models for N-heptane because everybody has been studying heptane for the last 30 years, and we have very good kinetic models. And for complex fuels, it's probably right. It's one of the most widely studied hydrocarbon fuels. So N-heptane, again, I'll always show these types of very simple sketches of molecules. So you don't see the carbon and hydrogens, they're implicit. But this is C7H16. The types of reactions that will happen will depend on the reactor temperature, and the system's reactivity will also depend on the reactor temperature and the nature of the chemical reactions. Now, the two types of reactions any molecule starts off with one is scission. Yeah, you can have a CC scission, CH scission, or you can have an abstraction reaction, abstraction of a radical. Typically, if it's oxygen is around, if it's oxidizing environment, the radical abstraction reactions are the most important ones. If we're pyrolyzing the fuel, meaning we're burning fuel or reacting fuel without oxygen, not necessarily burning, but reacting fuel without oxygen, it's pyrolysis. Then you have carbon-carbon scissions. So here we're just showing for an oxidizing environment, the first step could be an abstraction reaction. Now, this abstraction reaction can happen at any relatively low temperatures, maybe around 350, 400 degrees Celsius, so say 700 degrees, or 700 degrees Kelvin. And at low temperature, the abstraction can happen at a relatively slow rate, because at low temperature, rates are always slower. So initially, your fuel gets consumed initially by abstraction, and the radical has to undergo some further reactions. Now, at low temperatures, the radical cannot break apart on its own. It cannot undergo its own unimolecular scission reaction, so it has to have a bimolecular reaction with something else. In an oxidizing environment, it's typically oxygen. Okay, and this is the reaction we see here. R radical reacts with O2, and you form this molecule, peroxy radical. Don't worry about remembering all this today. We're going to go into the details of all these reactions. You'll go crazy with all these different reactions in a few days. But today, just understand, okay, the radical reacts with oxygen. You form another radical. We call this a peroxy radical. This radical undergoes isomerization. Isomerization means the hydrogen moves from another carbon atom to the peroxy group. So it's like, you can say isomerization, or you can say internal hydrogen abstraction. The molecule abstracts hydrogen from somewhere else on its molecule to make the peroxy group more stable. So you get that hydroperoxide, that OOH. But now the radical site moved back to the carbon chain. Then you react with oxygen again. And you form another peroxy group, OO. And then now the molecule is becoming quite heavy and bulky. It has a lot of oxygen. It has a radical site. So preferably what it starts doing, it can internally abstract hydrogen again, but then it undergoes a scission reaction. And in the end, after this whole sequence, we form something called a ketohydroperoxide, which breaks apart, very unstable molecule. It breaks apart to form some radicals, OH, an carbonyl radical, and a stable carbonyl, an aldehyde. Now, this whole scheme is what we call degenerate low temperature chain branching because one radical, fuel radical, ended up an OH radical and another carbonyl radical, which will go back and lead to further formation of radicals. This happens at relatively low temperatures. This happens even in the atmosphere. So actually our group around 2016, we started working with chemists in Helsinki University, Finland. And there they study atmospheric chemistry. And we started to see that the reactions that happen in the atmosphere are the same ones that happen in combustion systems, just the temperature is different. So this reaction scheme is responsible for the formation of aerosols. Whenever we emit hydrocarbons like gasoline vapors, or many times in a paint shop where they're painting cars and parts, metal parts, they have a lot of volatile chemicals, which are alkanes and branched alkanes and cycloalkanes. They go into the atmosphere and they start reacting by this scheme and they form aerosols, highly oxidized molecules, but the temperature is not high enough for them to fall apart and make more radicals. They just keep growing and growing and growing, and they eventually condense and they form like cloud condensation nuclei. They form these what we call secondary organic aerosol vapors, and very important in the climate because this has a cooling effect on the climate. So these researchers in Helsinki show how these molecules, if you don't have them in atmospheric models, you don't get the climate forcing right. But in the kinetics, the chemistry is the same as what happens in combustion engines. So yeah, you can see the parallels at low temperature are very similar to things that are happening in the environment. Then as the temperature increases, okay, the reactivity is increasing of your mixture. As temperature increases, reactions accelerate. That's Arrhenius law, right? So all of these reactions are increasing with temperature. More of the fuel is converted to radicals. They isomerize. They add O2 again. They isomerize. They form hydroperoxides. They break apart. And the reactivity is accelerating. But at higher, if you take, just again, the limits might here be, say, 300 degrees Celsius, so 600 degrees Kelvin, up to 900 degrees Kelvin. But in the middle, if we jump to a high temperature regime, like say about 1100 degrees Kelvin, so 800 degrees C, we have a different reaction scheme that comes important. The radical, that fuel radical that's made, now temperature is high enough for the CC bonds to break, for it to fall apart on its own. So this is what we call a beta scission reaction. We'll cover these again in detail. The radical just breaks apart. It forms an alkene, or an olefin, as we said, a double bonded molecule, and then another radical. And then this process continues. It's no longer chain branching, but it's just propagating the radicals. Eventually, you lead to things like soot and NOx because these alkenes build up. They form things like acetylene. Acetylene goes to form benzene. Benzene then goes to form your first aromatic hydrocarbons. And you get pyrene, and then you make soot. Okay, so you make soot from this high temperature combustion scheme. And high temperature, again, the reactions are accelerating as the temperature keeps going up. But it's a different mechanism at high temperature and at low temperature. At low temperature, it's peroxy radical chain branching. At high temperature, it's radical scission. But something happens in the middle, which is very peculiar, and very peculiar to alkane type fuels, okay? There's other types of reactions that come into play. And if you add oxygen, this peroxy radical, as temperature increases, it actually breaks apart before it isomerizes. So you form HO2 radicals and olefins. Sometimes you could form things like what we call cyclic ether molecules and OH radicals. And the main aspect of this is temperature was increasing when you went down this main pathway, and reactivity increased. But if you keep increasing temperature, all of these intermediate pathways come into play, and they decrease the overall reactivity of the system. In these schemes, you're not making two radicals anymore. You're only making one OH radical and one HO2. In the main scheme, the low temperature radical chain branching path, you had two radicals at the end. These intermediate schemes only make one radical. So one radical means less reactivity overall. And then we have this type of behavior you see here. This is what we call a negative temperature coefficient phenomena. So I'm ramping up the temperature in my reactor from, say, low temperature, 300 C to 600 C, 900 Kelvin. Then after that, the reactivity starts decreasing up till about 1100 Kelvin, and then it increases again. We call this negative temperature coefficient phenomena. It's very hard to predict because there's so many reactions that are happening. They're competing with each other. In addition, you have thermochemistry. If you see here, these reactions are reversible. So the R plus O2 making the peroxy, it can also go back to form radicals. That's governed by thermodynamics. Similarly, the second O2 addition, all these things are governed by thermodynamics as well. And we have to try to predict this. So we need accurate thermochemistry, we need accurate kinetics, we need to know that these pathways are there and what they're doing in the system. And we'll try to build a model later on, by Wednesday or so, to represent all this different phenomena. So besides the reactions, though, you need experiments, right? If I take an experiment which is a laminar premixed flame, where is it going to be in this graph? What temperature is a laminar premixed flame? High temperature, because you've already lit the flame. The flame is now propagating. A premixed laminar flame speed is a high temperature combustion phenomenon. The flame is already at high temperature, let's say 2000 Kelvin. It's trying to propagate upstream, so it's preheating the reactants upstream maybe by a few hundred degrees Kelvin. So they're starting to undergo high temperature reactions already. Any type of flame is a high temperature combustion phenomenon. You don't care about low temperature combustion. When do you care about low temperature combustion? Autoignition, before the flame is lit. So you inject in a diesel engine, you inject fuel into a hot air, because it's a compression ignition system. So you compress the mixture, the fuel, you compress the air in the cylinder. It might reach around 650 degrees Kelvin, 700 degrees Kelvin, and then you inject in the fuel. So it's injected into a hot environment. There's no flame yet, and the fuel and the oxidizer react until there's an ignition. This is what we call auto-ignition event. How about in a spark ignition engine? Is it high temperature or low temperature combustion? Okay, why? Okay, so if you hit, the ignition from the spark is a high energy input, and that's probably like 2500 degrees Kelvin or higher. It initiates a flame, right? And then that flame propagates through the cylinder. But when would you have low temperature combustion in an SI engine? Knock, yeah, exactly. So it's still important in an SI engine. Okay, say my spark is up here. And I have a mixture of fuel plus air, oxygen. In this, ideally what happens, right, is you fire the spark at, say, minus 15 degrees before top dead center, and a flame propagates out and burns the whole charge. So this flame starts burning the stuff up. It's moving to the end. It's slowly consuming everything in the cylinder. But then you can have knock. What happens in the knock scenario? Where does the autoignition happen? In knock. N-gas. It's called N-gas autoignition. N-gas means here, this mixture ignites. Why does it ignite? Because temperature and pressure are rising in this N-gas. As the flame is pushing it, it's compressing that N-gas. That N-gas was cold when the spark fired. It could not react, but as this flame keeps pushing it, it's like a compression ignition. And that gas, N-gas, auto-ignites, and you get knock, and that's bad for the engine. So we want fuels with high octane number, high resistance to this auto-ignition. High resistance. High resistance to reactivity at low temperature. So alkanes, N-alkane and heptane is very bad for autoignition because it can undergo this degenerate chain branching very well. Aromatics cannot. Olefins cannot. So they are very high octane. Yeah? Tetraethyl lead cannot. That's why it's very high octane. And we'll talk about this more, why different molecules have different octane. It's because the reactivity in the end gas is different depending on the structure of the molecule. So even an SI engine, it's important. Ideally, you'll have high temperature combustion in SI engine, but the phenomenon of knock is a low temperature combustion phenomenon. Gas turbine, most of the time, high temperature. Why? Well, you typically have a ring combustor, yeah. These flames are all lit, mostly initially by the pilot, and then you have a continuous burning process. It's typically a high temperature combustion phenomenon. But as you go more lean premixed combustion, these low NOx combustors, people are starting to study how chemical reactions already start happening before the fuel enters into the combustion chamber. Okay, so these are all the different reactions. The way we determine the types of reactions to put in a chemical kinetic model are typically based on reaction classes. Again, I can tell you, the top types of reactions that are possible are millions. So we cannot include all of them. So we classify the reactions into different classes, and then we can start writing out the reactions based on the types of reactions that are happening. And these are, we won't go into detail today, but this is 9 different classes of high temperature reactions that are possible. Unimolecular scission of the fuel, abstraction, decomposition of the radicals, isomerizations, abstraction then from the intermediates that are formed, and so on, how you deal with the intermediate olefins. And then at high temperatures, if we go to make soot, then I have to add more reactions for PAH formation, for the eventual soot formation. And at low temperature, even more reactions, more complicated. So reaction classes from 10 to 29 are all related to low temperature chemistry. So now you have alkyl RO2 addition, all different types of reactions with the peroxy radical, bimolecular reactions with intermediate radicals, cyclic ether formation, and then ketohydroperoxides. And we'll go into many of these, depending on your appetite. Some of them I'll go over in detail, others I won't, because it can get rather complicated. But again, in principle, at low temperatures, these are all the different reactions one would want to include in a model to make it comprehensive. If you're just simulating flames, don't waste your time with all these low temperature reactions. Just deal with the high temperature ones and get a good model. But if you want to deal with things like compressed ignition, auto ignition in the N gas, atmospheric chemistry. The other interesting ones are in the food industry, they study all these reactions a lot because of the auto-oxidation of fats and oils. So all food has very nice hydrocarbons, yeah? They're fats, yeah, and oils. And the structure of a fat and oil is what we call a triglyceride. So it's a carbon chain, which is like a hydrocarbon. You have a carbon chain, and it ends you have this it ends in these glycerol backbones, okay? Glyceride backbones. And I might have it a bit wrong because I'm not very good in chemistry, but yeah, and off the top of my head, I have to look at it. But it's these hydrocarbon chains with a glycerol structure at the end, and these 3 monoglycerides are stacked, 3 of them together. They call them triglycerides. And these fats and oils undergo the same types of reactions, yeah, at low temperature. So when you're cooking your oil, yeah, some of these carbon-carbon bonds are breaking. Sometimes there's abstraction reactions. If you leave the oil for a long time on the shelf, what happens to it? Anybody know what happens to your cooking oil if you leave it there for like a few months? It goes rancid, starts smelling bad, or if you taste it, it's a bit acidic. That's because auto-oxidation now happens not in the order of milliseconds like in an engine. It happens over months. So the same reactions are happening. They're just going on for weeks and months at a time. The oxygen in the air is slowly dissolving into the liquid, and it's starting to react. And what happens in an engine in a few milliseconds or microseconds, happens over months, and the oil starts to go bad. And whenever they're making these commercial products in the food industry, sometimes they heat them up and cool them down. So they try to understand how do these glycerides then, or triglycerides, behave, and how do they oxidize, and how does that determine then the shelf life of your fuel. So many different applications for the same chemistry. Okay, so we'll come to all that in detail. Let's start with the basic principles of what one needs to apply when we start building these kinetic models. So today we'll just cover the basics, thermochemistry and thermodynamics, and then the chemical kinetics that govern the chemical kinetic properties which are important for our system. Now, I'll go through most of this pretty quickly because I think you guys know it fairly well, just like a refresher. And of course, if you want to study it more, you have the notes to look at. So first, we need to know what is the heat of formation of a molecule, because the heat of formation is what's going to determine eventually the Gibbs free energy of reaction, the heats of reaction, and also the things like the heat of combustion. So thermochemistry is just our basic form of thermodynamics dealing with the chemical enthalpy related to individual molecules. So we define then the standard enthalpy of formation at room temperature and pressure, so 298 K and 1 bar. We define the standard enthalpy of formation of a molecule by taking a molecule and producing it from its elements. So this molecule, methane, the heat of formation of methane is based on the reaction to make methane from its elements, and it's made from carbon, graphite, and hydrogen. And the heat of formation is the delta H of this reaction. So the heat of formation of methane is minus 74.8 kilojoules per mole, or minus 17.98, minus 18 kcals per mole. And enthalpy is a function of state, so we don't need to necessarily make the molecule from its elements. We can even combine different reactions to determine the heat of formation of a molecule. So as an example, if we want to determine the heat of formation of carbon monoxide, we can get it from carbon dioxide. So carbon plus oxygen makes carbon dioxide. The heat of formation is from the heat of reaction. Its heat of formation of carbon dioxide is minus 94 kilocalories per mole. Then carbon monoxide, the unknown heat of formation, can be determined from the heat of reaction of carbon monoxide plus half oxygen makes carbon dioxide. We know carbon dioxide is 94. Then we can get the unknown parameter carbon monoxide based on this heat of reaction. The heat of reaction here is minus 67.6, so that the difference between the heat of formation of CO2 and the heat of reaction for the second reaction gives us the heat of formation of carbon monoxide, which is minus 26.4. This kind of thing we will use later on. We will use it when we have hundreds or thousands of species in a mechanism, and we want to get the thermochemistry data, the heat of formation of some unknown molecules. If we have other molecules, which we know this molecule reacts with, and we know their heat of formation, we can find the unknown quantities. So we can use, again, simple thermodynamics to make sure that our models are more accurate. Okay, then we should be clear that when we talk about a stable molecule, like an element like hydrogen, the heat of formation is always defined as 0 in the reference state. So, and that's because these molecules like hydrogen, stable molecules, are unreactive in their parent state. But if we take a molecule like hydrogen, we split it apart into radicals, 2 H radicals. The radicals, the H, has a heat of formation. So the heat of formation of H radicals is 52.1 kilocalories per mole. And this comes from the bond dissociation energy. So the bond dissociation energy between 2 H atoms to make hydrogen is 104.2 kilocalories per mole. So then the heat of formation of one of those is 52 kilocalories per mole. What is the difference between a radical and an ion? Anyone want to tell us? Are ions radicals? Are radicals ions? Are they the same thing? Different? Different? Tell. Okay. Yes?
Radicals are uncharged.
Yeah. So
Ions can be
that's the key. The key is we just have an unpaired electron. Yes? Repeat it, right? Yeah. So he says, yeah, the ions are charged molecules, positively charged, negatively charged. A radical doesn't have to be charged or positive or negative charge. It just has an unpaired electron, yeah. So many people sometimes think ion, they get these two things confused. Ion, we can have neutral molecules like CO2 and methane, which are ionized, yeah. They don't have unpaired electrons, but they can have a charge associated with them. Okay. Then the heat of combustion comes from the heat of formation of the elements or the molecules that are participating inside of a chemical reaction. And that's the one we care about. The most important reaction in combustion is the reaction of molecules with oxygen. So if we know the standard enthalpy of formation of a molecule participating in a reaction, then we can determine the heat of reaction. And the heat of reaction in a combustion system is what we call the heat of combustion. So the heat of combustion is the so-called energy that's released when a compound undergoes complete oxidation or complete reaction with oxygen under the standard conditions. Here we say Q combustion is also minus delta H combustion. And then we have minus delta H of the reaction, which is the stoichiometric coefficient of each element, each species multiplied by the heat of formation of that species and all summed up. So again, the example here given methane plus oxygen goes to form CO2 and water, the complete oxidation or the complete combustion. So the Q combustion is the heat of formation of the products minus the heat of formation of the reactants, which gives us then 802 kilocalories or kilojoules per mole, or 191.7 kilocalories per mole, or in mass basis, 12,000 kilocalories per kilogram of hydrogen. Similarly, you can do this for hydrogen. Sorry, this is for methane. For hydrogen, hydrogen plus half oxygen giving you H2O in the gaseous phase. Hydrogen plus oxygen gives us H2O in the liquid phase. We could have the heat of combustion for formation of the liquid. Hydrogen is 34,100 kilocalories per mole. For gaseous hydrogen, to form gaseous water, is 28,900 kilocalories per kilogram of hydrogen. Now, the heating value is something that we describe, which is typically given on the mass basis of fuel. But of course, thermochemistry is always on the molar basis of the fuel. There's one important thing to know. We have two different types of heating value, the lower heating value and the higher heating value. Who wants to say what the difference is? Yes, there? Right. So are you recovering the energy for the condensation of gaseous water to liquid water? That's heat of condensation gives us energy, right? You can remove energy from the system through the heat of condensation. So when would we want to use the lower heating value? Which type of systems would you think it's relevant? So in engines, most engines, IC engine, right? We talk about the lower heating value. Because in an engine, you burn your fuel, you make water in the vapor, and we just dump that in the exhaust, right? We don't really recover it. Where do we recover? So which systems would we use a higher heating value? Huh? Gas turbine? Thermal power plants. Yeah. Tell us what happens in a thermal power plant. Yeah, so whenever you have a gas turbine together with a steam turbine, right? So combined cycles, boilers. So many boilers, we run the steam through a steam cycle, and then you recover the heat from the condensation of that steam back, the gaseous steam back to liquid. So that always, typically, yeah, different engineers in different industries, they'll say, come to us, you're working in automotive engines, why are you talking about the lower heating value? You should use a higher heating value. Well, it depends on the system, right? So most of the time, again, you're working in aircrafts and transportation and engines, we use a lower heating value. If you're working in power plants with combined cycles or steam cycle, we'll use the higher heating value. So this is a table of the heats of combustion, the lower heating values, okay, of different fuels. And this is from Professor Law's book, yeah, Combustion Physics, 2006. I'm sure many of you might be using this one in your classes. There's some interesting things to note here. So, of course, the best fuel is hydrogen on a mass basis, 28,672 calories per gram, or kilocalories per kilogram. For the lower heating value of hydrogen, methane is the second best, 11,958, okay, calories per gram. And then we start to talk about our oxygenated fuels like we saw here, methanol, carbon monoxide. The first thing you note, methanol is simply methane with one oxygen, but you drop the heating value a lot on a mass basis because that oxygen does not provide any additional heating value. So that heat of reaction, hydrocarbon plus oxygen go to CO2 and water. If the oxygen is in the hydrocarbon, it doesn't add anything to the heating value. It's still ending up at the same product of CO2 and water. Then we can also note here some interesting things, like here you have propane, butane, pentane. So propane was C3, butane is C4, pentane is C5. The heating values are pretty much the same. They're all around 110 calories per gram, kilocalories per kilogram. So homologous fuels, so all these alkanes, you add carbon. On a mass basis, you're adding more carbon. You're adding proportionally the same amount of energy for each carbon or CH2 group that you're adding. So the LHVs are similar for different types of alkanes. Similarly, for different types of alkenes, if you look here, like butadiene is 106. Then, well, sorry, we only have one alkene here. We don't have many to compare against. But you'll see, butadiene is a dialkene. Other types of dialkenes would be the same. Aromatics, toluene and xylenes, they're all in this range of about 107, 107 and a half calories per gram. Sorry, 10,700 calories per gram. And in kilocalories per kilogram, closer to 9,700 for toluene and for xylene. So we see here, and again, more alkanes are shown here, N-octane, isooctane, hexadecane, all pretty much the same. So if we're talking best fuels, alkanes are very good, right? Anywhere from 10,500 to 11,000 kilocalories per gram. Aromatics, a bit lower, about 10% lower in terms of their energy density or their heat of combustion. And hydrogen is the best. Ammonia, where's ammonia around? On a mass basis, anybody know? So we said hydrogen was 120. That was megajoules, right, per kilogram. So divide by about 4 for kilocalories. Ammonia, I think, is, I don't know off the top of my head. I'm going to say it's a fair bit lower. It's about 20 megajoule per kilogram. Okay. So a factor of 6 or so less. Yeah. Okay. Then these are This is a heat of formation. From the heat of formation, we can also get from the change of enthalpy, we can get the heat capacity. So change of enthalpy is simply the heat capacity as it changes with temperature. So dH is Cp delta T. And if we want to determine the heat of formation or the heat of reaction at another temperature, we can take the heat of formation of a molecule at standard conditions and then integrate Cp delta T over the temperature range of interest. So we commonly do this when we're trying to predict thermodynamic properties. We can predict thermodynamic data for heat of formation of a molecule at room temperature and room pressure. But in combustion systems, we need all these values at high temperature, at 200 C, 400 C, 800 C. So we simply get that from the Cp of the molecule integrated over the temperature range of interest. And then we fit that with the NASA polynomials. You guys will have seen those. We'll talk more about those tomorrow, those NASA polynomials and how we can fit them against this data. And again, the whole aspect of heats of formation and change of heat of formation as a function of temperature is path independent. So if you take a reactant and you heat it up and then you conduct your reaction, you come to a final state. If you do the same thing, you take your reactants, you heat them up. You react them first and then you heat up the products and come to the same state. In the end, the state at the end doesn't matter how you reach it. These are path independent functions. So from the heats of formation, we can then go to the things like the Gibbs free energy of reaction. This is the other important condition that we care about when we're talking about kinetics and chemical kinetic systems. So if we take a system and we want to determine its equilibrium state, we can use the Gibbs free energy of reaction. The Gibbs free energy of reaction says that for some system, let's say a reactant A plus B going to R plus Q with some stoichiometric coefficients, lowercase a, lowercase b, lowercase r, and lowercase q, the equilibrium will be determined by minimization of the Gibbs free energy of the system. And this minimization of the Gibbs free energy system is described by the change in the Gibbs free energy of the reactants and the products, and that's simply the change in the heats of formation, and T times the change in the entropy of formation of the molecules. And this then can also be defined as the equilibrium constant, KEQ, which is the concentrations of the products raised to their stoichiometric coefficients divided by the concentration of reactants raised to their stoichiometric coefficients. And this equilibrium constant we need to use. We will use it a lot because based on every reaction in our mechanism, we need to determine the equilibrium condition from the Gibbs free energy of reaction. That together with the equilibrium constant can also help us to determine concentrations of species that are unknown in our system. So here we have, again, at equilibrium, at this equilibrium constant condition where the reactants are going to products, the products are going to reactants at equal rates. The Gibbs free energy is H minus T delta S. This is also equal to minus RT ln of the equilibrium constant. So we can calculate this equilibrium constant, KEQ, as also from the Gibbs free energy. So KEQ is exponential minus delta G over RT. And we will use this in every chemical kinetic model because this KEQ is simply the forward rate constant divided by the reverse rate constant. So I said all these kinetic parameters for every reaction have to be provided. Well, in principle, we only need to provide them in one direction because every reaction has to be governed by the equilibrium of the system. So if you have a forward reaction and we know the equilibrium constant, which can come from minus delta, exponential minus delta G over RT, we can then, this can be a known quantity for all the species in the system of the reaction. This can be a known quantity. You can also get the reverse rate constants for that system. But even before we start using it in the form of reaction kinetics, we can use very simple things like Gibbs free energy of the system to determine what are going to be the stable products if I take a fuel and oxidize it or start heating it up to a high temperature. So this is what we call Francis diagram. This is showing delta G, minimal delta G at different temperatures. I have an extra G here. Sorry, this should be just delta G less than 0 is a favored reaction. Delta G is equal to 0 is at equilibrium. Delta G greater than 0 is a disfavored reaction. And this is based on the change in Gibbs free energy is minus entropy times the change in temperature plus VDP plus the change in chemical potential of the system, which is the chemical potential of each molecule multiplied by the number of moles of those molecules. So here we see a chart. If we take, say, ethane, shown here, C2H6, below 1100 degrees Celsius, ethane is a very stable molecule. Sorry, this is 1100 degrees Kelvin. Ethane is very stable if we were to just keep it on its own for a fixed period of time without elevating the temperature further. Ethane would be more stable than the products such as ethylene and acetylene. But if we start heating up the mixture above 1100 degrees Kelvin, ethane will decompose to form ethylene. And ethylene will be more stable, okay, the most stable form together with hydrogen. So ethylene plus hydrogen will be more stable than ethane. And then we start heating it a bit more, and you see here at around 1400 degrees Celsius, the line for acetylene and hydrogen starts to cross the one for ethylene. So at equilibrium conditions, acetylene will be the most stable species. Acetylene and hydrogen will be more stable than forming ethylene and hydrogen. So you can already start to see, forget about kinetics, just from the thermodynamics of the system, at different temperatures, what would be the product species that are formed. This is, again, a similar diagram. Rather than showing it in terms of Francis diagram, we can plot now molar concentrations of species as a function of temperature based on the Gibbs free energy of the system calculated for all these different species. So let's say we have methane at 1 atmosphere and we start changing the temperature. So at around 700 degrees C, methane will start to decompose a bit. You'll start to form hydrogen, and you'll start to form other intermediate species like benzene, ethylene, ethane, and so on. And if we heat up this reactor to, say, 1300 degrees Celsius, we can start to form a lot more hydrogen at equilibrium, and methane will be converted to form hydrogen, and its concentration would be decreased. And we use this many times. So there's one system that comes to my mind, the pyrolysis of methane. So many of you might have heard of turquoise hydrogen, okay? Turquoise hydrogen is when you take methane and you pyrolyze it, and you want to make preferably carbon, elemental carbon, and hydrogen. No oxygen, no CO2 formed. This graph tells us right away, in order to do this reaction, to get enough hydrogen, I got to be at a pretty high temperature, yeah? Even forget about the kinetics, just by thermodynamics, if I want to start to form more hydrogen than methane, I got to come to above something like 1100 degrees Celsius. At the same time, though, I'm going to be making benzene and acetylene. I might want to minimize the formation of benzene, so then I heat up my reactor even further to, say, 1500 degrees Celsius. I'll get more hydrogen, but now I'm going to get also a lot of acetylene. And then acetylene will eventually, if I draw this chart even further, at higher temperature, you'll have carbon formation, elemental carbon, which I have not shown in this chart. And then if I go to very high temperature, I start to dissociate to form the radicals. So all of this to say, even in a simple pyrolysis system, we can use things like just minimizing the Gibbs free energy to find out what is the optimal temperature to operate my reactor at to get a certain number of products. Okay, then another principle we need to be worried about or concerned about is the change in the equilibrium as the temperature changes in the system. So we know, again, the Gibbs free energy is a function of temperature and the equilibrium constant, which is related to the heat of formation and the entropy of formation of the system. Van 't Hoff equation gives us a change in equilibrium constant then as we change the heat of reaction in the system. So if we have an endothermic reaction, it tells us that the equilibrium shifts towards the reactants as the temperature increases. So for an endothermic reaction, the equilibrium constant is increasing with temperature, and for exothermic reactions, the equilibrium constant is decreasing. So as you increase temperature, the exothermic reaction is becoming disfavored as temperature increases. Now, most of our reactions in combustion are exothermic. So yeah, we don't, as you increase exothermicity of the reaction, your overall conversion will decrease because your equilibrium constant is decreasing. And then finally, the other important factor in all of this is the change in temperature, but also the change in pressure, what this does to the equilibrium of the system. So this effect of pressure is determined by Le Chatelier's principle. So the equilibrium of your reaction is determined by the change in number of moles in the system. So if we have something like a unimolecular reaction, if you increase the pressure, which is decreasing the volume, you'll always shift your reaction to the side where you have the fewer moles of gas, or the fewer number of molecules. And vice versa, if you decrease the pressure, then you shift to the side with more moles of gas. So if you have a unimolecular reaction, again, C2H6 goes to form C2H4 plus H2. At equilibrium, we would want to do this reaction at high pressure or low pressure? Yes, at low pressure, we will favor the formation of the product species. As we go to high pressure, you're going to want to go back to the reactants. Sometimes we have reactions that are bimolecular in nature, two reactants going to form one product. Well, those reactions at equilibrium are going to be favored at higher pressure. In the methane pyrolysis, CH4 going to carbon plus hydrogen. This is a reaction. Ideally, you would do it at low pressure. Of course, you can't go, it's harder to go less than 1 atmosphere, then you need vacuum vessels and stuff. So yeah, at low pressure, we would typically, unimolecular reactions, we do them. In a refinery, we have things we call crackers, thermocracker units. So this is actually a very common reaction in a refinery. Ethane to form ethylene, because you take natural gas, they separate out the ethane, and then they have methane. Sorry, they take natural gas, which is a mixture of methane, ethane, propane. They separate the ethane, they separate the methane, and then they do a thermocracking process. This is a thermocracker. There's no catalyst. It's done in a thermocracker, no catalyst. Just heat up your ethane to about 1,050 degrees Celsius at low pressure, about 1.2 bar, 1.2 atmospheres, and you get ethylene. And why would you want ethylene? Plastic, polyethylene. Everything we have is made from ethylene today, yeah? So chemical engineers, ExxonMobil develops chemical kinetic models just for this thermocracking process. Try to optimize, because you don't always only get ethylene. Sometimes you get some acetylene, sometimes you get carbon, you get other hydrocarbon intermediates. They want to make ethylene, that's the desired product. They don't care about the hydrogen, actually. They usually flare it off or use it somewhere else in the refinery. But yeah, so these processes are used in many different industries, not only combustion. In a combustor, though, we're typically going to high pressure because you have fuel plus oxygen. you want to favor the formation of products, CO2 and water. If the water condenses out, CO2 is the main gas, then you typically want to go to high pressure. You can get better reactivity. You also get faster reaction rates at high pressure. So all of that is to determine the equilibrium state of your system, okay? The equilibrium state is what happens after a certain amount of time is surpassed and we have gone past the kinetically controlled regime. However, in most combustion systems, we rarely reach the equilibrium state because, especially in an IC engine, the exhaust valve might open before you reach the equilibrium state. So things become frozen, so to speak, somewhere in this kinetically controlled regime. So the fuel wants to react, eventually reach equilibrium state, but oftentimes the process ends before we reach the equilibrium state because, again, either there's not enough time or there's different phenomena that are happening which are determining this. For example, flame propagating through a medium is a rapid chemical reaction that's trying to get to equilibrium, but oftentimes the flame is moving, and before you can even reach the equilibrium point, the flame has reacted and already moved on to a different point. So the flame, because of its transient nature, is always operating in a kinetically controlled regime. Most of the stuff here, most of the stuff of interest to us happens in this regime of kinetics. And that's where we like flame propagation, auto-ignition, even most of the formation of pollutants like soot and NOx and PAHs happen in this region. Also, most of the reactions that are low temperature, they need a lot of time before they can reach equilibrium, and that time is simply not afforded in a practical system. Nevertheless, many of you might work on systems like turquoise hydrogen, like cracker units, chemical reactors, where equilibrium products is sufficient. We did a big project with Shell on the gasification of vacuum residual oil, okay? This is vacuum residual oil is that stuff at the bottom of the barrel. So after you got the light fuel out, the diesel, the gasoline, the jet fuel, even the marine gas oil, that stuff at the very bottom is called vacuum residual oil. It's like road tar, pretty much, okay? It's the stuff that if you don't want to get anything out of it, you put it on the roads, like asphalt, yeah? This is a gasifier. Into this gasifier, you feed in vacuum residual oil. You feed in some oxygen, pure oxygen, and some steam, water, okay? Pure oxygen. They don't feed in air because they want the temperature to be very high. And with oxygen, you can get higher temperatures than if you have air because of the nitrogen that's a dilutant gas. So this is the other way. So all of these things are fed into this vessel. We call it a vessel, but this thing is like 60 meters tall, okay? Huge, okay? This is a massive gasifier, and these are some of the biggest units in the world. 60 meters tall, probably about 8 meters in diameter. Refractory aligned, so it's a steel vessel, but it's coated with refractory ceramic materials. And what happens here, they ignite with a pilot, and you form this massive flame at the top of the gasifier. The flame is probably like 5 meters long, okay? And what this is doing is creating a very high temperature environment in the rest of the gasifier. So the flame might be around 2,000 degrees Celsius, but very quickly, this whole thing is heating up, and it's about anywhere from 1,600 degrees Celsius at the top to maybe 1,400 at the bottom, yeah? And the goal at the end is to make syngas, CO and hydrogen. This is syngas. And then what they do, they take this and they put it in a gas turbine. And they make power. You burn this to make power. And why would you do this? Well, you can't burn vacuum residual oil. It's so heavy, it's so nasty, you can't burn it in a gas turbine. So they do all this crazy, fancy gasifier just to make syngas, to make power in the end. Now this process, a 60-meter tall pipe, let's say, 8-meter diameter pipe, from 1600 C from the top to 1400 degrees C at the bottom, they wanted us to model the kinetics of this system. And first of all, this was extremely nasty stuff. So the R&D department of Shell made a project for 3 years. We developed kinetic models of this. Then when it came to develop, we developed a kinetic model. We can predict the CO, the hydrogen, we can predict the soot, the methane. And then we gave it to the plant engineers. And the plant engineers said, this is all a waste of time. We use equilibrium and it's good enough. Yeah? Because this thing here, 1600 to 1400, you can see, it happens over like 5 seconds. Yeah? So indeed, like, everything that's happening at the top is kinetically controlled. But then you have some intermediate products that are formed, and then your VRO starts reacting over this like 5 seconds, say 50 meters in length reactor in a homogeneous environment, and they just use equilibrium to calculate the final gas composition, and it's pretty good. It's actually almost as good as the kinetics, yeah? Actually, we predict pretty much the same CO and hydrogen using equilibrium and using detailed kinetics. And the equilibrium, of course, you can put this into a CFD model. Well, they don't even need a CFD model. They don't care about CFD even. They just model this as a simple plug flow reactor, yeah, with something going in and equilibrium concentration of products coming out. And that's how they've designed these reactors at industry scale. And they have them in China, they had them in Europe, but they got decommissioned. They have them now in Saudi. Okay, we had to justify our existence. There's some molecules that you cannot predict with equilibrium, yeah? Like the CH4, the methane, the PAHs. These things are intermediates that are somewhat frozen in 5 seconds. There's some intermediate fraction because the chemical reactions are frozen. And they're in like, methane might be there in less than 1%. This might be there in ppm range, yeah? These, and again, CO is there in maybe 40%. This might be 60 or 58% hydrogen. So the major products are equilibriumly controlled. But these minor species like methane, PAHs, that are there in very low concentrations are kinetically controlled. So I mean, the point is, I'm trying to say is, depends what you want to predict, right? If you care to predict all these minor things that are happening in a reactive system, yes, you can use kinetics. Kinetics are important. But many times the industry doesn't even care, right? They just want to know what are the major products that are coming out. I design my system according to that, and it's good enough, yeah? And again, for this system, we justified because methane, they didn't want to release methane in the exhaust. It's a greenhouse gas. PAHs lead to form soot, so they used our model in the end. But again, don't build a model unless you really need it, yeah? Sometimes these equilibrium calculations are perfectly good enough. Okay, what time is the break? Now? Yeah? Okay, let's take a pause. And then we'll wrap it up with some basic kinetics.